Right now, at this very moment, you are sitting inside a galaxy, not near one, not orbiting one from a safe distance, not observing one through a telescope. Inside one, you are embedded in the body of a vast, slowly rotating structure that stretches approximately 100,000 light years from one side to the other. Not miles, not kilometers, light years. Units of distance so large that they require light itself, the fastest thing in the known universe, to define them. Light travels at nearly 300,000 kilometers every single second. In the time it takes you to blink, light has already covered roughly the entire distance between the Earth and the Moon. In a single year, traveling without stopping, without slowing, without rest, light crosses about 9.5 trillion kilometers. That is one light year. One unit of measurement. The Milky Way is 100,000 of those. Even light, moving at its incomprehensible speed, takes 100,000 years to cross the galaxy you call home. Humans, by comparison, have never truly left the solar system. Our fastest spacecraft, launched nearly 50 years ago, with all the ambition our civilization could muster, has traveled far enough that it now exists in the thin, cold space between the solar wind and the true interstellar medium. And that journey has taken half a century of travel. That probe has covered less than 0.1% of the distance to the nearest star. We are, in the most literal and honest sense, just getting started. So the question is not just about engines or fuel or time. The question is about what it really means to exist inside something this large, and what it would genuinely take to cross it. If light itself takes 100,000 years to cross the Milky Way, how long would it take us? If you enjoy calm, deep explorations of space like this one, consider subscribing. There is much more to explore. There is a particular kind of stillness that descends on a person the first time they genuinely try to feel the scale of the universe, not just understand it from a distance, not just accept the numbers as trivia, but truly and honestly try to let the size of it land somewhere in their chest. It is not a frightening feeling, as you might expect. It is something quieter, something like the feeling of standing at the edge of the ocean on a dark night, knowing that the water continues beyond everything your senses can confirm, and finding, to your own surprise, that the enormity of it is somehow calming rather than terrifying. That is the space we are going to inhabit for the next little while. This narration follows a single question from its most basic surface, all the way down into the deepest layers of physics, engineering, human possibility, and meaning. The question is deceptively simple. The answer is everything but. By the end, you will have a number, several numbers actually, depending on the technology we assume. But more importantly, you will have a genuine feel for what those numbers mean and for what it says about us that we can calculate them at all while still being unable to act on them. Let us begin where all honest cosmic conversations must begin, with the thing itself. The Milky Way galaxy is, in the truest sense, our home at the largest scale. Not just Earth, not just the solar system, not just the local group of stars, but the entire rotating, luminous, ancient structure in which all of those things live. And when you try to describe it accurately, the words that present themselves most readily are words like vast and immense and incomprehensible, and none of them actually work. They gesture at the idea without landing it. So let us try something more careful. The Milky Way is a barred spiral galaxy. That means that instead of simple spiral arms emerging directly from a rounded central core, those arms emerge from the ends of an elongated bar of stars that cuts across the center of the galaxy. Seen from above, from a truly impossible, godlike vantage point far outside our galaxy, the Milky Way would look like a softly glowing pinwheel, maybe 60,000 light-years across for the main disk, with a central bar perhaps 27,000 light-years in length, and several spiral arms curling outward from the ends of that bar into the surrounding space. There is a bright, dense central bulge at the middle, a roughly spherical population of older stars called the halo surrounding the whole structure, and a disk of younger stars, gas, and dust where most of the ongoing star formation happens. The disk itself, where we live, is approximately 100,000 light-years from edge to edge. In some directions, Measurements push that number toward 160,000 light-years because the disk is not perfectly flat or perfectly circular. It warps and buckles slightly as it ages, like a spinning coin gradually losing its perfect symmetry. But for our purposes, the canonical number is 100,000 light-years. The thickness of the disk varies. In the outer regions where our solar system lives, the disk is roughly 1,000 to 2,000 light-years thick. In the central regions near the bulge, it swells to perhaps 12,000 light-years. It is not a sphere. It is not a perfect disk. It is something organic and irregular and ancient, the way all real things in nature tend to be. Within that structure live somewhere between 100 billion and 400 billion individual stars. The uncertainty in that estimate is itself telling. We cannot count them individually any more than you could count the grains of sand in a desert by looking at it from a plane. The number 200 billion is used most commonly as a working estimate. 200 billion stars. Our Sun is one of them, a yellow dwarf of entirely average size, age, and brightness, sitting in what is called the Orion Arm, one of the galaxy's minor spiral arms, approximately 26,000 light-years from the galactic center. We are not at the center of the galaxy, which might have some romantic appeal, but would also expose us to intense radiation and gravitational chaos from the supermassive black hole that sits at the core. We are not at the outer edge, drifting in the sparse, lonely reaches beyond the main structure. We are, in a very comfortable spatial sense, middle class. We live in the suburbs of the galaxy, on a quiet, unremarkable road, orbiting a quiet, unremarkable star. And that star, our Sun, is itself orbiting the center of the galaxy. Everything in the galaxy orbits everything else, or rather, everything orbits the collective gravitational center of the whole system. The Sun moves at roughly 220 kilometers per second along its galactic orbit. That is not a speed you could ever feel. It produces no wind, no G-force, no sensation of any kind. You cannot feel the galaxy turning beneath you any more than you can feel the Earth turning under your feet as you sleep. But it is happening, and has been happening, for the entire 4.5 billion year history of our solar system. At that speed, the Sun takes approximately 225 to 250 million years to complete one full orbit of the galactic center. Astronomers sometimes call this a cosmic year or a galactic year. Our solar system has completed roughly 20 of these orbits since it formed. The first orbit was completed during an era when the most complex life on Earth was still single-celled organisms floating in shallow, ancient seas. By the time the 20th orbit, our current orbit, comes to a close, another 250 million years from now, the continents will have shifted into configurations that would be unrecognizable to us, and whatever lives on Earth at that point will likely bear no resemblance to us. The galaxy is old. It is roughly 13.5 billion years old, which makes it nearly as old as the universe itself. The universe is estimated at about 13.8 billion years. The Milky Way began forming within a few 100 million years of the Big Bang, when the first clouds of hydrogen and helium started collapsing under gravity into the early precursors of stars. It has been building itself, star by star, merger by merger, for nearly all of cosmic time. One of the most useful tools for making the size of the galaxy real to a human mind is analogy, even though every analogy eventually breaks down. Consider this one. If you shrank the Milky Way galaxy so that it fit inside a standard football stadium, roughly 100 meters across, the solar system would be smaller than a single atom. Not a grain of sand, not a bacterium, an atom. The Earth itself would be 1/10,000,000th the size of that atom. And on that infinitely small mote of scale-shrunken matter, we are trying to ask questions about the stadium. This is the thing we are asking about crossing. Not a highway, not an ocean, not a continent, a living, rotating, ancient structure of 200 billion suns. He built across 13.5 billion years, 100,000 light years from one edge to the other. Now let us talk about humans, and in particular, let us be very precise about where humans fit into all of this, because the contrast is really the heart of the entire question. Our species, Homo sapiens, has existed for roughly 300,000 years. Our anatomically modern ancestors were already present in Africa before the last glacial maximum. before the migration out of Africa, before the development of language, art, and ritual. 300,000 years is a genuinely long time from a human perspective. 7,500 generations, enough time for our anatomy and cognition to stabilize into the form they hold today. But on the timescale of the galaxy, 300,000 years is essentially nothing. If the entire history of the Milky Way were compressed into a single calendar year, modern humans would have appeared in the last 12 seconds of December 31st. Written human history, everything we know, happened. All the civilizations, all the wars, all the philosophy and mathematics and music would fit into the last half second of that year. The entire industrial era, the entire age of science, the entire period of space exploration, a tiny fraction of that half second. We are extraordinarily new, and our technology is newer still. The first object humanity ever launched into Earth orbit was Sputnik 1 in October of 1957. That is fewer than 70 years ago. 70 years before that, the internal combustion engine was barely a decade old. 200 years before that, James Watt was still refining the steam engine. Our species has been building civilization for a few thousand years and has been engaging in recognizable science for roughly 4 centuries. We have been a spacefaring civilization, loosely defined, for less than 70 years. In the context of a 13.5 billion-year-old galaxy, we are not even a rounding error. We are less than a rounding error. We are a trace amount of activity in a single arm of a single galaxy among hundreds of billions of galaxies in the observable universe. Our physical reach into the cosmos reflects this. The farthest humans have traveled from Earth is the Moon during the Apollo missions between 1969 and 1972. The average distance from the Earth to the Moon is about 384,000 kilometers. Pluto, the dwarf planet at the outer edge of the classical solar system, is on average about 5.5 billion kilometers from Earth. The New Horizons spacecraft, which performed a flyby of Pluto in 2015, took 9.5 years to reach it, 9.5 years to cross the inner solar system. The nearest star to our Sun is Proxima Centauri, at a distance of approximately 4.2 light-years, about 40 trillion kilometers. Nothing we have built can reach it in a human lifetime. Voyager 1 is the farthest human-made object from Earth. Launched in September of 1977, it carried with it a golden record, a disk containing sounds and images from Earth, a kind of message in a bottle tossed into the cosmic sea. In 2012, after 35 years of travel, it crossed what scientists call the heliopause, the boundary where the solar wind finally yields to the interstellar medium. It entered interstellar space for the first time. It was a genuine milestone in human history, and yet, by any cosmic standard, it is still practically next door to us. As of the time this script was written, Voyager 1 is approximately 24 billion kilometers from the Sun. That sounds enormous. 24 billion kilometers. But in light-year terms, it is about 0.0026 light-years. The nearest star is 4.2 light-years away. Voyager 1 has been traveling for nearly 50 years and has covered roughly 0.06% of the distance to the nearest star. Think about that for a moment. Nearly 50 years of travel. The probe is so far away that a radio signal traveling at the speed of light takes over 22 hours to reach it, and it has not yet covered 0.1% of the distance to the nearest star. Voyager 1 is currently moving at roughly 17 kilometers per second. That is a genuinely impressive speed by any earthly measure. It is about 50 times faster than the fastest bullet, about 60 times faster than a commercial aircraft at cruising speed. But 17 kilometers per second is approximately 0.0057% of the speed of light. It may help to find some earthly texture for the speed of 17 kilometers per second. If you were traveling at that speed across the surface of the Earth, which is of course impossible, but bear with it, you would circle the entire planet in roughly 37 minutes. You would travel from New York to London in just under 20 minutes. These feel fast. They are fast by any standard that human life has equipped us to judge speed. And yet, at that same speed, traveling toward the nearest star instead of around the Earth, you would not arrive for 73,000 years. The vast majority of human civilizations that have ever existed have not yet lasted as a species for 73,000 years, let alone as individual cultures. Now let us apply Voyager's speed to our question. The Milky Way is approximately 100,000 light-years across. 1 light-year is about 9.5 trillion kilometers. 100,000 light-years is therefore roughly 950 quadrillion kilometers. At 17 kilometers per second, which is Voyager's current speed, the time required to cross the galaxy from one end to the other is approximately 1.7 billion years. 1.7 billion years, not 1.7 billion days, not 1.7 billion weeks. Years, 1,700 million years. The age of the Earth is 4.5 billion years. 1.7 billion years is more than a third of that. It is the time separating us from the Proterozoic eon, when the most complex things on Earth were simple, early multicellular organisms. It is before the Cambrian explosion, before fish, before plants on land, before everything we associate with complex life. At our current best speed, crossing the galaxy would take longer than complex multicellular life has existed on our planet. This is not a discouraging fact. It is simply an accurate one, and it is the foundation we need to build the rest of this story on. Let us begin to climb the ladder of speed and watch how the numbers change. Suppose that in the future, the not-so-distant future, perhaps within the next century or two, humanity develops technology capable of accelerating a spacecraft to 1% of the speed of light. 1% of 300,000 kilometers per second is 3,000 kilometers per second. That is about 176 times faster than Voyager 1. No current propulsion concept can reliably achieve this speed, but it is not ruled out by any fundamental physics. It is an engineering challenge rather than a physical impossibility. At 1% of the speed of light, crossing the 100,000 light-year diameter of the Milky Way would take 10 million years. 10 million years ago on Earth, our distant ancestors were early hominids. They were not yet Homo sapiens, not yet even Homo erectus. They were small, bipedal, forest-dwelling primates with brains roughly a third the size of ours. No fire, no tools of any recognizable kind, no language. All of recorded human history, from the first writing in Mesopotamia to the present moment, covers roughly 5,000 years. 10 million years is 2,000 times longer than all of recorded human history. Achieving 1% of the speed of light is not simply a matter of building a bigger rocket. The fundamental constraint of chemical propulsion, the kind we use today, is that the energy density of chemical fuels cannot produce the exhaust velocities needed to achieve these speeds. No matter how efficiently you burn hydrogen and oxygen or any other chemical propellant, the physics of chemical reactions sets a ceiling on exhaust velocity that is about 4,000 meters per second. To reach 1% of light speed, 300,000 meters per second, requires an entirely different kind of propulsion. Nuclear propulsion, either fission or fusion, could theoretically bridge part of this gap. Controlled nuclear fusion for spacecraft propulsion remains, for now, a technology of the future. At 10% of the speed of light, 30,000 kilometers per second, the crossing would take 1 million years. 1 million years still encompasses more change, more history, more evolution than human minds are designed to readily comprehend. But the number is at least now within a range where human imagination can begin to reach for analogies. 1 million years ago, Homo erectus was spreading across Asia and Africa. Modern humans were still hundreds of thousands of years in the future. At 50% of the speed of light, 150,000 kilometers per second, the journey would take 200,000 years. 200,000 years ago, anatomically modern humans had just appeared on Earth. At 90% of light speed, 270,000 kilometers per second, the crossing would take approximately 111,000 years. At 99% of the speed of light, the crossing time from the perspective of an outside observer drops to just over 100,000 years. But here is where something extraordinary enters the picture, because the outside observer's perspective is not the only perspective, and the other perspective is one of the most mind-bending revelations in the entire history of physics. Albert Einstein was 26 years old when he published his special theory of relativity in 1905. He was working as a patent clerk in Bern, Switzerland, and in a single year, a year that has become legendary in the history of science, he produced 4 papers, any one of which would have secured his reputation as a major physicist. The special theory of relativity was one of those 4. Its implications are still being unpacked more than a century later. One of those implications is time dilation. The concept sounds abstract until you sit with it long enough for it to become physical. Time is not constant. Time does not flow at the same rate for all observers in all situations. The rate at which time passes for any given object depends on that object's velocity relative to other objects. An object moving very quickly through space relative to a stationary observer experiences time more slowly than that stationary observer does. At everyday human speeds, the speed of cars or planes or even orbiting spacecraft, the effect is so tiny as to be completely imperceptible. The difference in clock rates between someone on the ground and someone in a satellite is measured in microseconds per day, tiny, negligible for most purposes, though significant enough that GPS satellites must be corrected for relativistic effects or they would drift out of accuracy within hours. But as speed approaches the speed of light, the effect becomes anything but negligible. The mathematical relationship is captured in what is called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz, who helped develop the mathematics that Einstein then placed in a broader theoretical context. The Lorentz factor tells you how much time dilation a moving object experiences relative to a stationary frame. At 10% of the speed of light, the Lorentz factor is approximately 1.005. Time for the traveler runs about 0.5% slower than for the stationary observer. Over a 10 million year journey, at that speed, that amounts to about 50,000 years of subjective time difference. Meaningful at that scale, but not transformative. At 50% the speed of light, the Lorentz factor rises to about 1.15. The 200,000 year galactic crossing would feel, to the traveler, like about 173,000 years. Still, an incomprehensible span of time. At 90% the speed of light, the Lorentz factor climbs to approximately 2.3. The 111,000 year journey feels to the traveler like about 48,000 years. Better, but still far beyond any human lifetime, and far beyond any ship or civilization one could realistically imagine sustaining. At 99% the speed of light, the Lorentz factor is approximately 7. The 100,000 year journey would feel, from inside the spacecraft, like about 14,000 years of subjective experience. At 99.9% of the speed of light, the Lorentz factor reaches approximately 22. The crossing time compresses to around 4,500 years of subjective experience. Still far beyond a human lifetime, but beginning to approach timescales that a civilization, as opposed to an individual, might theoretically organize around. At 99.99% of the speed of light, the Lorentz factor is approximately 224. The crossing feels, to the traveler, like about 450 years, a few generations, and at 99.999% of the speed of light, a speed so close to the cosmic speed limit that we are splitting hairs with decimals, the Lorentz factor climbs above 700. The 100,000 year galactic crossing would be experienced inside the spacecraft in approximately 140 years. 140 years, a single, extended human lifetime, a journey begun by one generation might be completed by its grandchildren if they somehow survived. The galaxy that looks 100,000 light years wide to an outside observer becomes, from inside, an extremely relativistic spacecraft compressed to something like 140 light years. The universe, at those speeds, physically shrinks in the direction of travel. This is not an illusion. It is a genuine geometric effect called length contraction, and it is as real as anything in physics. But there is an important caveat that must not be glossed over. All of this relativistic compression applies only to the traveler's subjective experience. To everyone who remains behind, on Earth, in the solar system, or in the galaxy, the journey still takes 100,000 years. Every person the traveler has ever known dies within the first century of their departure. Every institution, every civilization, every record of anyone they ever loved is dust before they have traveled 1/10 of the distance. The traveler arrives at the other side of the galaxy, perhaps still biologically intact, only to find that the universe has aged 100,000 years around them. The sun is older. Earth, if it still exists, is unrecognizable. Whatever civilization they left has had 100,000 years to evolve, collapse, rebuild, and transform into something bearing no relationship to what was there when they left. They arrive not in their future, but in a future so distant it is effectively another universe. All of this discussion of extreme speeds and time dilation comes with a caveat that must be examined honestly, because it is one of the most fundamental walls in all of physics and engineering. Getting to any significant fraction of the speed of light requires energy, a great deal of energy, and as you push closer to the speed of light, the energy required does not grow linearly, it grows without bound. The closer you are to the speed of light, the more energy is needed for each additional increment of speed, and the growth approaches infinity as the speed approaches light speed. This is not an engineering problem that better materials or more powerful engines will simply solve. It is a constraint built into the fabric of space-time itself. To put numbers around it, accelerating a spacecraft of just 100 metric tons to 90% of the speed of light requires roughly 6.3 times 10 to the 22nd power joules of energy, humanity's current total annual energy consumption. All the electricity, all the fossil fuels, all the nuclear power, all the renewable energy generated globally is roughly 600 exajoules. Accelerating our 100-ton spacecraft to 90% light speed would require about 1,000 times the total annual energy consumption of the entire human civilization. The most theoretically efficient propulsion concept physicists have identified for near light speed travel is the photon rocket, a system that converts matter to energy with perfect efficiency through matter-antimatter annihilation and uses the resulting photons as thrust. It is the most efficient engine physically possible. It extracts energy from mass at the maximum rate nature permits. Even the perfect photon rocket, given the mass ratios involved, would need roughly equal masses of fuel and payload to reach the extreme speeds we have been discussing. Humanity currently produces antimatter in particle accelerators at the rate of a few nanograms per year. A nanogram is 1/1000th of a gram. To produce enough antimatter fuel to cross the galaxy at those speeds would take, at current production rates, approximately 10 to the power of 21 years. That is 1 billion trillion years. The universe is only about 14 billion years old. We would need to run our particle accelerators for roughly 70 billion times the current age of the universe to produce enough fuel. Even if we imagined antimatter production scaled up by every order of magnitude that optimistic futurism could propose, the scale of the challenge remains foundational, not incidental. Even getting to any significant fraction of the speed of light carries staggering energy costs from the interstellar medium alone. At relativistic speeds, each particle of interstellar hydrogen becomes a tiny but significant projectile, hitting the spacecraft with the energy of a high-speed particle accelerator experiment. Over 100,000 light-years, the cumulative effect of these collisions on any material spacecraft would be severe. The shielding required would be massive, which increases the ship's mass, which increases the fuel required to accelerate it, which increases the mass further, a feedback loop that pushes energy requirements even higher. There is no known solution to this that does not involve either extraordinary materials, science far beyond current capability, or some form of active magnetic deflection of charged particles, which itself requires enormous sustained energy across millions of years. Given the constraints of physics and energy, some thinkers have proposed approaches to interstellar and intergalactic travel that work around these walls rather than through them. These approaches accept that the speed of light is unattainable and the energy costs of near light speed travel are practically prohibitive, and they ask, given those constraints, what can we actually do? The generation ship is perhaps the most ancient and enduring of these concepts. The underlying logic is simple. If the journey takes longer than a human lifetime, send a community rather than a crew. Build a ship large enough and self-sufficient enough to sustain a human population indefinitely. The travelers who arrive at the destination are the descendants of the travelers who departed. The journey spans not one lifetime, but many generations. The appeal of the concept is real. It requires no exotic physics. It does not need antimatter or laser sails or relativity. It needs only engineering and time, two things that, in principle, are available to a sufficiently patient and capable civilization. The practical challenges are where the concept begins to reveal its true depth. A generation ship would need to function without failure for timescales that dwarf any engineering project in human history. The oldest continuously operational human-made structures are stone buildings a few thousand years old. A generation ship crossing the galaxy at any realistic speed would need to function perfectly for millions of years. Every mechanical system, every electronic system, every biological support system would need to be maintained, repaired, and if necessary, redesigned by successive generations who have never received any outside instruction or supply. The social and psychological challenges are, if anything, more daunting than the mechanical ones. What would it mean to be born into a ship and know from childhood that you will never leave it, that your parents never left it, and your grandparents never left it, and in all probability, your children and grandchildren and 1,000 generations of your descendants will never leave it either? The destination, the other side of the galaxy, is not something any living person on the ship will ever experience. It is a mission passed down through the generations like a sacred obligation, a story told and retold across millennia, a purpose that must somehow remain coherent and motivating through the rise and fall of cultures, languages, and belief systems that we cannot even imagine. No civilization in recorded history has maintained a coherent institutional purpose across even 10,000 years. The generation ship would need to maintain one across millions. Cryogenic suspension, or cryosleep, addresses these challenges differently. Rather than letting time pass for the passengers, it attempts to stop time for them. The passengers are placed in a biologically suspended state, body temperature dramatically reduced, metabolism essentially halted, and they travel across cosmic distances without aging, without experiencing the intervening years, waking only upon arrival. The problem is that we do not yet know how to do this for humans. The primary challenge is ice crystal formation. When biological tissue is frozen, water inside the cells can form ice crystals that tear cell membranes apart. Reviving a frozen human being, at present, reliably kills them. Research into suspended animation and the biochemistry of extreme cold tolerance has made genuine progress in recent decades, even without reaching the threshold of full human cryosuspension. Most scientists have successfully preserved and revived individual organs at low temperatures for extended periods. The cooling of core body temperature, a state called therapeutic hypothermia, is already used in medicine to reduce brain damage after cardiac arrest or stroke. Several organisms in nature solve related versions of this problem. The wood frog of North America can survive being frozen solid during winter, with ice forming within its tissues. And Thor, each spring completely unharmed. Tardigrades can survive extreme desiccation and temperature variation through a mechanism involving the replacement of water with a glassy sugar matrix that protects their cellular structures. These examples suggest that the problem is not theoretically insurmountable, but the complexity of a human brain, with its 100 billion neurons, its trillions of synaptic connections, and the exquisitely precise chemical and electrical state that constitutes identity, memory, and personality, presents a challenge of a different order. A third approach abandons the question of human biological survival entirely and asks instead, what is really the point of crossing the galaxy? If the goal is to observe it, to study it, to sample its stars and document its civilizations, if they exist, then perhaps the most efficient and realistic approach is not to send biological humans at all, but to send machines, probes, artificial intelligence systems embedded in small, fast, resilient spacecraft capable of collecting data and transmitting it back over cosmic distances. The Breakthrough Starshot initiative, announced in 2016, proposed exactly this kind of mission, not for the Milky Way as a whole, but as a proof of concept aimed at Proxima Centauri, our nearest stellar neighbor. The proposal is to use a large array of ground-based lasers to accelerate a fleet of gram-scale spacecraft, essentially microchips, attached to light sails thinner than a human hair, to 20% of the speed of light. At that speed, the probes would reach Proxima Centauri in approximately 20 years, fly through the system, collect images and basic measurements, and begin transmitting data back to Earth at the speed of light. Extended to galaxy crossing scales, AI probes would still take enormous spans of time. At 20% light speed, roughly 500,000 years. But they would not age. They would not need food or water or breathable atmosphere or social interaction. They would simply continue, patiently, year after year, century after century, millennium after millennium, recording and transmitting. The self-replicating probe concept pushes this idea even further. First described mathematically by the polymath John von Neumann in the context of automata theory, a von Neumann probe is a machine capable of gathering raw materials from its environment and using them to manufacture complete copies of itself. A fleet of such probes, launched toward nearby stars, would arrive, replicate, and each copy would set off toward different nearby stars. The expansion would be exponential. A single wave of self-replicating probes could, in theory, explore every star system in the Milky Way within a few tens of millions of years. A long time by human standards, but a small fraction of the galaxy's total age. This concept raises profound questions that are not merely engineering questions. If such machines are possible in principle, and if the laws of physics apply consistently throughout the universe, then any sufficiently advanced civilization that arose before us in this galaxy could theoretically have already covered it with such probes. The fact that we have detected no such probes, no signs of artificial structures, no anomalous signals, no evidence of anything manufactured beyond our own solar system, is one version of the Fermi paradox, the puzzle of the great cosmic silence. Either we are truly among the first technological civilizations in this galaxy's history, or the others have chosen not to spread visible infrastructure, or the von Neumann probe concept runs into obstacles we have not identified, or something else is happening that we do not yet understand. This puzzle does not have a comfortable resolution. It simply sits there, in the data, asking to be taken seriously. There is another dimension to the crossing problem that tends to receive less attention than propulsion and energy, but is no less profound: communication. As a spacecraft travels away from Earth, the time required for a radio signal to travel between the spacecraft and home grows at the rate of 1 year per light year of distance. A spacecraft that has traveled 1,000 light years from Earth would wait 1,000 years for a reply to any message it sent. At the midpoint of a galaxy crossing, 25,000 light years from the starting point, the communication lag would be 25,000 years each way, 50,000 years for a single exchange. For all practical purposes, the spacecraft would be completely on its own. No instructions, no updates, no help of any kind could arrive on any timescale meaningful to the mission. Whatever intelligence, human or artificial, was running the mission would need to be completely self-sufficient in every conceivable scenario for the entire duration of a crossing that takes millions of years. There is also an entirely different way to think about the communication problem across galactic distances, one that turns it into something almost philosophical. Suppose a probe or a generation ship or any human artifact were to successfully cross the galaxy and arrive at the other side. What would it find? We genuinely do not know. Our telescopes can observe the far side of the galaxy only approximately through the obscuring dust and gas of the disk. We know there are stars there. We know the density of stellar populations varies. We do not know, at the level of detail that would matter for a destination, what is there. The travelers would be crossing toward a destination selected not from direct knowledge, but from projections and models, knowing that any course correction based on new information would take thousands of years of round-trip communication to implement. They would be in the most literal possible sense, sailing blind across an ocean with no shore in sight, it guided only by mathematics and faith in the physics they departed with. And yet, this has been, in miniature, the story of every great human voyage of exploration. The Polynesian navigators who crossed the Pacific did not have GPS or radio contact with home. They had star maps and ocean current knowledge, and the courage to sail beyond what had been confirmed. The first humans to cross the Bering Land Bridge into the Americas had no map of what lay ahead. Columbus did not know what he would find. In each case, the journey was made on the best available knowledge, and in each case, the reality at the other end was different from anything the travelers had imagined. The crossing of the Milky Way, in this sense, is not a categorically different kind of enterprise from what our species has done before. It is simply the same kind of enterprise at a scale so much larger that it requires a fundamentally different relationship with time, energy, and the meaning of civilization itself. It is also worth considering what the galaxy would look like from the inside during such a crossing, because the visual experience would be unlike anything humans have ever seen. We imagine space as dark and empty, punctuated by the occasional bright point of a distant star. That is an accurate description of our local neighborhood, where stars are typically several light years apart. But the Milky Way is not uniformly structured. The central bulge is far denser than the disk. Some regions of the disk have higher concentrations of young, hot, blue stars, molecular clouds, vast, cold regions of gas and dust where new stars are being born create dark patches against the stellar background. Star clusters, both open and globular, dot the landscape. Nebulae glow with the light of ionized gas. A ship crossing the galaxy over millions of years would pass through all of these environments, sometimes in relative darkness, sometimes bathed in the glow of dense stellar regions, sometimes navigating through the tendrils of a molecular cloud. The Milky Way from the inside, traversed over geological timescales, would be a journey through every kind of environment the galaxy contains. Not a monotonous black void, but a constantly changing landscape of light, gas, and gravity. None of this diminishes the challenge. None of this makes the numbers smaller, or the energy requirements more tractable, or the biological and social obstacles less severe. The galaxy is still what it is, ancient, enormous, and essentially indifferent to our plans for it. But understanding it clearly, in all its beauty, and all its scale, and all its genuine intractability, is itself a form of engagement with it. Every civilization that has ever looked at a challenge it could not currently meet has had to decide whether to look away or to keep looking, keep measuring, keep building the understanding that future generations might one day act on. There is a hard conversation to be had now, and it deserves honesty rather than soft pedaling. Crossing the Milky Way in any meaningful sense that involves human beings arriving alive and intact at a destination across the galaxy is not merely very difficult. It is, for all practical purposes, almost certainly beyond the reach of our civilization as we can currently envision it, and possibly beyond the reach of any civilization permanently bound by the physics of our universe. The numbers are simply too large. At our current technology, the journey takes 1.7 billion years. At plausible near-future technology, it takes millions of years, even at the most extreme fractions of light speed that physics permits, fractions that would require energy inputs approaching infinity to achieve. The outside world journey, time remains around 100,000 years, with all the civilizational transformation that implies. It is worth trying to feel, honestly, and without false comfort, what it means to be in this position. We live on a planet that is roughly 12,700 kilometers in diameter. The solar system in which that planet sits is roughly 2 light-years across when you include the outer cometary cloud. The distance to the nearest star beyond our sun is 4.2 light-years. The diameter of the Milky Way is 100,000 light-years. The distance to the nearest large galaxy, Andromeda, is approximately 2.5 million light-years. The observable universe stretches about 93 billion light-years in all directions. We have explored, physically and directly, a few hundred kilometers of the ocean floor. We have landed humans on the moon. We have sent probes to every planet in our solar system, and one probe to the edge of interstellar space. where it is barely one light day from home. In the face of these numbers, there is a tendency either to despair or to inflate, to say either that we are nothing or to insist that we are uniquely special, destined to overcome. But there is a third response that feels more honest, and it is the one that the night sky has always offered to those who spend real time looking at it. There is a thought that tends to arrive slowly, somewhere in the middle of long conversations about cosmic scale. It is not a comfortable thought, exactly, but it is a settling one. Consider what had to happen for this conversation to be possible. Approximately 13.8 billion years ago, the universe began in an event we call the Big Bang, a state of extraordinary density and temperature from which all matter, energy, space, and time emerged and began to expand. In the first few minutes, the lightest elements formed: hydrogen, helium, and traces of lithium. For hundreds of millions of years, the universe was dark and uniform, filled with slowly cooling gas. Then, the first stars ignited. Those first stars were enormous by modern standards, burning hot and fast, living for only a few million years before exploding in supernova. Those supernovae scattered into space the heavier elements forged in the star's cores: carbon, oxygen, nitrogen, iron, silicon. These heavy elements seeded the next generation of stars with richer chemistry. They formed the dust clouds that collapsed into rocky planets. They became the raw materials of geology and biology. On a rocky planet, orbiting a second or third generation star, about 4.5 billion years ago, some of this chemistry crossed a threshold no one fully understands yet. The threshold from complex chemistry to self-replicating chemistry, from non-living process to life. That first life was single-celled, fragile, and confined to thin films in shallow seas. But it persisted, it diversified. Over billions of years, it evolved into forms of increasing complexity, increasing capability, increasing sensitivity, and then, in the last 300,000 years, the final blink of the cosmic eye, one lineage of large-brained, bipedal mammals developed the capacity not just to survive, but to ask why, to measure things, to look at the sky and calculate, to sit here and wonder, how long would it take to cross the Milky Way? The hydrogen atoms that make up your body were forged in the Big Bang, nearly 14 billion years ago. The carbon and oxygen and nitrogen that make up your cells were forged in the cores of ancient stars that died before the sun was born. You are, in a very literal and non-metaphorical sense, made of stardust, made of the galaxy you are asking about crossing. The Milky Way did not just produce you as an afterthought. You are a product of its full history, every generation of stars contributing to the atoms that now constitute your consciousness. And that consciousness, improbable, brief, fragile, extraordinary, is the only thing in the observable universe currently known to be aware of the universe's existence. The Milky Way does not know it is a galaxy. The stars do not marvel at the distances between them. The spiral arms do not contemplate their own geometry. The supermassive black hole at the center does not feel the gravity it exerts. None of it experiences itself. None of it is aware. Only we are. Only here, in this quiet corner of an outer arm, does the universe currently look at itself and say, I am here. I am large. I am ancient. I am beautiful. There is a well-documented psychological phenomenon among astronauts who have seen the Earth from orbit. It has been called the overview effect, a shift in perception that occurs when you see the Earth as a whole, small, borderless object against the black of space. Astronauts describe the experience as transformative in a way that photographs do not fully convey. The Earth looks fragile. Its atmosphere appears as the thinnest of films, barely visible at the horizon as a faint blue haze. Its surface, marked by no political boundaries, no signs of the billions of lives lived upon it, looks at once utterly ordinary and completely miraculous. Now, extrapolate that feeling outward, not to orbital distance, not to the moon, but to the far side of the galaxy, 100,000 light-years away, from which the entire solar system would be invisible, and our galaxy itself would appear as nothing more than a faint smudge of light among other faint smudges. At no point in this scaling journey is there a vantage from which the Earth appears physically significant, and yet the beings doing the scaling, doing the imagining, the calculating, the feeling, are the only things in that entire field of view known to be thinking anything at all. We are physically insignificant and cognitively extraordinary simultaneously. Neither fact cancels the other. Both must be held at once. The honest picture of where we are in the long arc of cosmic time is one that requires both humility and patience. Our technological civilization is extraordinarily young. If we date it from the Industrial Revolution, it is perhaps 250 years old. If we date it from the invention of writing, it is perhaps 5,000 to 6,000 years old. The universe is 13.8 billion years old. Our civilization, at its most generous estimate, is less than 100,000th of 1% of the universe's age. Civilizations that survive and grow over very long timescales, measured in millions or billions of years, not thousands, may develop relationships with energy and matter that are simply inconceivable from where we stand today. A civilization that has had access to the energy of its entire solar system for millions of years is not meaningfully comparable to a civilization that has been burning coal for 2 centuries. The constraints that feel fundamental to us, the impossibility of convenient antimatter production, the extraordinary energy costs of near-light speed travel, may be, from the perspective of a mature and ancient civilization, as quaint as the constraints faced by ancient humans who had not yet discovered fire. We do not know that such civilizations are possible. We do not know that our civilization will survive long enough to grow into one. But the history of science is a history of walls that turned out to be doors. The question of crossing the Milky Way has, at this point, given us several answers. At current technology, 1.7 billion years. At 1% of light speed, 10 million years. At 10%, 1 million years. At 99.999% of light speed, with relativistic compression, about 140 subjective years, during which 100,000 years pass for the outside universe. Practically speaking, today, impossible. In any foreseeable future, effectively impossible. In some distant, hypothetical future, where physics and engineering have reached limits we cannot currently envision, deeply, profoundly challenging, and still attended by the loss of everything and everyone the traveler has ever known. Perhaps the most honest thing to say about crossing the Milky Way is that it is, for us right now, a thought experiment and not a plan. It is a question that we ask not because we expect to answer it with a launch date and a mission profile, but because the act of asking it, of following it honestly into the physics and the numbers and the engineering and the philosophy, teaches us something true about where we are. It is the kind of question that a species asks when it is young and curious and just beginning to understand the scale of the context it finds itself in. The question does not need to be answerable to be worth asking. The asking is the point. The asking is what we are doing when we are most fully ourselves, most fully the peculiar, brilliant, disoriented, curious creatures that 4 billion years of evolution somehow produced on this small, warm planet at the edge of an ordinary galaxy. We did not choose to be born into this universe. We did not choose its scale, or its age, or its indifference to our presence within it. We simply woke up inside it, the way you wake up in a room you have never seen before, and started trying to understand what kind of room it is. And the room, it turns out, is 100,000 light years across, and we are still standing in the doorway. There is one more dimension of the Milky Way that deserves mention, because it makes the galaxy even larger than the luminous disk alone suggests. Surrounding the visible disk and bulge is a vast, roughly spherical region called the dark matter halo. Dark matter is not a theoretical placeholder. It is a real component of galaxies, detected through its gravitational effects on the motion of stars and gas, and on the bending of light passing through and around galaxies. The dark matter halo of the Milky Way extends perhaps 100,000 to 300,000 light-years beyond the visible edge of the disk in all directions. When you include the halo, the Milky Way may be as much as 600,000 light-years in total diameter. The luminous disk, the part we can actually see, is the bright, compact heart of a much larger gravitational structure. Even the crossing of the visible disk alone takes 100,000 years for light. The full structure is 6 times larger. Orbiting this extended halo are numerous satellite galaxies, smaller collections of stars gravitationally bound to the Milky Way. The most famous of these are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as faint, detached patches of sky. The Large Magellanic Cloud is about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years distant. These are neighbors, satellites, companions in the gravitational family of our own galaxy system, and they are still multiple times the diameter of the visible Milky Way disk away from us. Some physicists and speculative thinkers have proposed solutions that bypass the speed constraint entirely, not by going faster, but by going differently. The most famous of these is the Alcubierre drive, proposed in 1994 by physicist Miguel Alcubierre. The concept involves contracting space-time in front of a spacecraft and expanding it behind, creating a bubble of flat space-time that the spacecraft rides like a wave. Within the bubble, the spacecraft is technically stationary relative to its local space. It is the space itself that is moving. Since it is space moving, not the spacecraft, the speed of light restriction does not technically apply. The spacecraft inside the bubble could, in principle, arrive at a distant destination faster than light would in normal, unmodified space. The Alcubierre drive is not ruled out by general relativity. It is, in fact, a genuine solution to Einstein field equations, but it requires something called exotic matter, a form of matter with negative energy density in quantities so enormous and of a type so speculative that most physicists consider it physically unrealizable. Subsequent research has shown that even if exotic matter exists, the quantities required for any practical Alcubierre drive are comparable to the mass energy of a planet, composed entirely of negative energy matter, which is itself a concept that has never been observed anywhere in nature. The Alcubierre drive is a beautiful piece of mathematics. Whether it corresponds to any physical reality remains deeply uncertain. Let us also pause on the pattern of the speed and time numbers, because there is something powerful in seeing them laid out together and letting them speak for themselves. At our current fastest speed, 17 kilometers per second, 1.7 billion years. At 1% of light speed, 10 million years. At 10%, 1 million years. At 50%, 200,000 years. At 90%, 111,000 years. At 99%, from the traveler frame, 14,000 subjective years. At 99.9%, 4,500 subjective years. At 99.99%, 450 subjective years. At 99.999%, 140 subjective years. Each step up in speed requires enormously more energy than the last, and the energy requirements approach infinity as speed approaches light. There is no comfortable middle ground. The speeds that make the crossing humanly survivable require energy inputs that are essentially infinite. The speeds that are conceivably achievable leave crossing times of millions of years. What kind of civilization would actually attempt such a crossing? This question does not get asked enough, but it sits at the center of the whole enterprise. A civilization that is merely curious about what lies on the other side of the galaxy has better tools, telescopes, probes, radio signals, than a crude crossing mission. The only scenario in which crossing the galaxy becomes a genuine necessity rather than curiosity is one in which Earth, the solar system, or the entire local region of the galaxy has become uninhabitable, and the crossing represents survival rather than exploration. In 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, likely engulfing the inner planets. This is the most predictable long-term, existential threat our planet faces. Addressing it requires not galaxy crossing, but solar system migration, moving civilization to the outer solar system or to another nearby star. The galaxy crossing, in this framework, is not something driven by necessity for billions of years. It is a question about the very distant future of a civilization that has already solved most of the problems we currently consider existential. There is something quietly clarifying about that framing. The question of crossing the Milky Way is not, in any immediate sense, a question we need to answer for our survival. It is a question we ask because we are the kind of beings who ask questions that extend far beyond immediate necessity. It is worth lingering on what it might actually feel like to attempt such a crossing, even in the mind. Imagine you are aboard a ship leaving the solar system on a crossing of the Milky Way. The sun, the planets, the entire world of human experience begins to shrink behind you. Within a year of travel, at a significant fraction of light speed, the sun is just the brightest star in the sky, no longer discernibly different from hundreds of other bright stars. Within a decade, it is indistinguishable from the stellar background. You have entered the open disk of the galaxy, surrounded by stars in every direction, the distances between them still enormous. You travel for centuries. The constellations slowly distort as you move through the disk, familiar patterns dissolving and reshaping over timescales that no human civilization has ever observed. The center of the galaxy, off to one side, grows gradually brighter, its dense core distinguishable from the surrounding stars. You pass through regions of higher stellar density, through thin gas and dust clouds, past the occasional stellar nursery, glowing with the light of newborn stars. And then you are on the far side, 100,000 light years from where you started, looking back across a faint streak of light that is the disk of your home galaxy, seen edge on from a vantage no human has ever occupied. That image exists only in the mind, but the mind is real, and its capacity to reach there across 100,000 light years and 100,000 years of time is itself a form of crossing that no spacecraft has yet equaled. The Milky Way is 100,000 light years across. Light takes 100,000 years to cross it. We, with our brief lifetimes and our early technology and our beautiful, relentless curiosity, cannot cross it. Not today, perhaps not for millions of years, perhaps not ever in any way that would be recognizable as a crossing. But we can measure it. We can hold its scale in our minds, imperfectly but genuinely. We can feel the weight of what it means to be here, inside it, small and warm and conscious. Looking outward, there is a mathematical concept sometimes used to describe the relationship between a civilization and the universe it inhabits. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. The scale classifies civilizations by their energy use. A Type 1 civilization harnesses all the energy available on its home planet: solar energy, geothermal energy, wind, ocean currents, the full energetic output of its world. A Type 2 civilization harnesses the full energy output of its star, something like the energy of the Dyson sphere concept, an enormous structure surrounding the star and capturing its light. A Type 3 civilization harnesses the energy of its entire galaxy. We are, by Kardashev's measure, currently a Type 0 civilization. We use only a small fraction of our own planet's available energy. The transition from Type 0 to Type 1, in optimistic estimates, might take a few hundred years. The transition from Type 1 to Type 2, perhaps thousands of years. The transition to Type 3, the energy of the galaxy, is so far in the future and so dependent on so many technological and social developments we cannot predict that the timescale is essentially open-ended. And yet, a Type 3 civilization, by definition, would have access to the energy required to do things like cross the galaxy. The Kardashev framework is not a plan, but it is a map of the territory, and it tells us clearly where we are, at the very bottom of the first rung of a very long ladder. The stars themselves have a lifespan. Our sun will live for approximately 10 billion years total, of which roughly 4.5 billion have passed. It has about 5.5 billion years remaining. The most massive stars in the galaxy live only a few million years before exploding as supernovae. The smallest, faintest red dwarf stars burn so slowly and so cool that they may live for trillions of years, far longer than the current age of the universe. In the very far future, after the last massive stars have burned out and the universe continues to expand and cool, the only stars still shining will be these ancient red dwarfs, quietly converting the last of their hydrogen into helium across timescales that dwarf everything else in cosmic history. Any civilization that hopes to persist long enough to truly explore the galaxy in the leisurely, multi-billion year sense will likely have migrated to the vicinity of a long-lived red dwarf long before the sun's eventual death. The galaxy is not static. It is evolving, aging, slowly running down toward an endpoint of cold and darkness billions upon billions of years from now. The window for life as we know it, organic, carbon-based, dependent on stellar light and warmth, is long by human standards, but finite by cosmic ones. Perhaps the most quietly astonishing thing about the question of crossing the Milky Way is not that the answer is so large, but that we know the answer at all. That, from our small, warm, improbable position in a minor spiral arm, using nothing but mathematics, physics, and instruments we have built in the last few centuries, we can calculate with genuine precision how long such a journey would take, what physical effects the travelers would experience, what energy would be required, and what the galaxy they are crossing actually looks like in structure and composition. We have never left the solar system. We have never seen the galaxy from outside, and yet we know its diameter, its mass, its age, its rotation rate, the number of its stars, the location of its central black hole, the structure of its spiral arms, and the behavior of the space-time through which a crossing spacecraft would travel. That knowledge was not given to us. It was earned over centuries by people who looked carefully at things that were far away and asked precise questions and recorded honest answers and built the understanding one layer at a time, generation after generation, until we arrived at this moment knowing things about the galaxy that no one in human history before the last 100 years could have known. Whatever comes next, whatever technologies emerge, whatever understanding deepens, whatever journeys future generations attempt or abandon, this capacity, this insistence on measuring and understanding and not looking away from the honest scale of things, is the foundation everything else is built on. The galaxy turns. The stars drift imperceptibly slowly through the long dark. 100 billion suns live and die across 100,000 years of light, and somewhere in a spiral arm near the outer edge, something made of ancient stardust looks up at the night sky and wonders, and in wondering becomes, for a moment, something more than the sum of the atoms it is made of. That something is us, and in the full and honest measure of this universe, that is not nothing. That, if we are willing to feel it, is everything.